Okay, here's the go through for the mechanics multiple choice questions. We've started with quite a tricky one here. So the table contains information on 4 wires, and we've got the stiffness. This is the spring constant, don't get that confusion, newtons per meter here is your clue, of each wire, and the maximum strain energy stored in the wire when extended to the breaking point. Okay, each wire has the same initial dimensions in the base Hooke's law. Which wire extends the least before reaching its breaking point? So what you need to understand here is that the energy stored, I'm going to write energy here to avoid confusion with the E, is a half k E squared. Small e is the extension. So what we're looking for is the extension that will store this amount of energy. So if we rearrange this, we get E squared is the energy times 2 divided by the spring constant. So the 4 different answers we've got here for E squared are 2 times 1 over 4, so 2 times the energy, which is 1, divided by the spring constant 4, and then we've got 2 times 1 over 9, then we've got 2 times 3 over 16, and 2 times 3 over 25. So hopefully you can see from that that this is a half, this is 2 ninths, this is 6 sixteenths, and this is 6 25ths. We're looking for the smallest extension, so we're looking for the smallest of those 4 numbers. This is E squared, but we're not actually calculating the extension, we're only working out the smallest one. So the smallest E squared will give us the smallest E. These numbers are not the easiest, but hopefully you can see that 6 over 25 is less than 6 over 16. 2 over 9 is less than a half. So then you're left with these 2 numbers. Obviously you can just put this in a calculator, but 2 over 9 is 6 over 27, which is smaller than 6 over 25. So the answer is B. Question 2. So we've got a 4 Newton load suspended from 2 parallel springs. Like this, the spring constant of each spring is 20 newtons per meter, and we've got to calculate the elastic energy of the system. So if we see the elastic energy, you probably think straight away this is going to be E equals half k E squared, but we need to work out the extension to do that. So we need to do F equals ke, E equals F over k. The force is 4 newtons, but the trap in this one is that the spring constant, each spring is 20 newtons per meter. They're in parallel. That means this system is twice as hard to pull down, so the spring constant of the system is 40 newtons per meter. So the extension will be 0.1 meters. If we go back to this equation, the energy stored will be a half times the spring constant of the system, which was 40, times the extension of the system, which is 0.1 squared, which is 20, times 0.01, which is 0.2 joules. So this answer is B. What you could have done alternatively is to imagine that this 2 newtons is hanging off each of the 2 springs individually, and then add those 2 together, but that would have ended you obviously back to the same answer, B. Okay, question 3. So a steel wire has a cross-sectional area of 0.5 millimeters squared. The Young modulus is 2 times 10 to the 11 pascals. It obeys Hooke's law. What load must be suspended from the wire to produce an extension which is 0.1% of the original length? So this is a Hooke's law question, so we've got E equals FL over AE. And if we rearrange that, that gives us F equals EAE over L. The Young modulus is 2 times 10 to the 11. The cross-sectional area is 0.5, that's millimeters squared though, so that's 10 to the minus 6. And then we've got E over L here at the end, so it hasn't given us an E or an L, but it has got 0.1% of the original length. So that's 10 to the minus 3, 1,000th of the original length, E over L. And if you stick all that in your calculator, you will find that comes to 10 to the 2 newtons, which is 100 newtons. Answer C. Okay, question 4. Again, quite an unusual question, quite a tricky one to think about. So we've got this material, we've stretched it, so you can see the arrows on the line. It started off at the origin, it's been stretched. This is the elastic portion here where the line is straight. Then we've got into the plastic region, and then you've taken the load off again and it's come back down this line, and ended up longer than when it started because there's been a plastic deformation. And then the question asks us, what's the increase in thermal energy of the sample? Well, what's gone on here is that we've extended the wire with the area under this line here. So the total energy that we've put in to get the line up to here is P plus Q plus R. But then we've, so if you like, the energy that you've had to put in to stretch that wire is P plus Q plus R. But then as the wire comes back again, we get this energy R back. So the R comes back out again, and P plus Q is the energy that's not come back out again. That's the energy that's lost in the wire, which is the increase in thermal energy of the wire. So that answer is B. Okay, question 5. Also want to make you think quite hard. So two masses hang at rest from a spring as shown in the diagram, and the string separating the masses is burned through. So we're going to break that string. I don't know why we're burning it, not just cutting it, but let's not worry about that. Which of the following gives the accelerations of the two masses as the string breaks? So I'm going to draw another little diagram here to try and give myself a bit more space. So here's our two masses initially. This is our 2 kilogram mass here. So the forces on this before we start are 2g downwards and 2g upwards, which is why it's stationary. This one here is 2g is the tension in the spring, in the string, plus of course the mass, which is another 1g. So the force upwards from the spring must be 3g. So when we then cut this or burn through this string, all of this disappears. Now this mass is now falling downwards. It's 2 kilograms with a force down of 2g. So of course this will just fall with an acceleration of gravity. So B is definitely not the right answer. But you see, it's unfortunately it's given us 3 options here of 1g downwards. So the tricky bit is to work out the acceleration upwards. If you look at this one now, we've got a 3g force upwards initially because the spring is stretched to create that force. So we've got 3g upwards. We've still got the weight going downwards of 1g. So the resultant force upwards is 2 times gravity. The mass is 1 kilogram. So the acceleration is 2g. So that answer is C. Okay, question 6. Just a little bit more straightforward, but still not easy. So we've got a wire of length L, cross-sectional area A, stretched by an extension of E by a tensile force, which they've not told us about, and the Young modulus of the material is E. Which expression gives the elastic energy? So the elastic energy is a half Fe, but we haven't got F, so we need the Young modulus equation, which is E equals FL over AE. Again, be careful here, this is not the energy, this is the Young modulus. So we need to rearrange this to get a value for F, or an expression for F. So F equals EAE over L. Then we can go back to this one and say that the energy stored is a half times EAE over L times E, so E squared, and that gives you the answer A. Question 7. So two vertical copper wires, so we've got two wires of the same material here, X and Y, equal length, joined as shown. Y has a greater diameter, as you can see in the diagram, and the weight is hung from the bottom. which of the following is correct? So the strain in X is the same as the strain in Y. Well, they're both carrying the same load here, so they're going to have the same force on them. So X will stretch more than Y. The stress in Y is greater than the stress in X. So Y has got a bigger cross-sectional area. So the force divided by the area is the stress. The bigger area means a lower stress. The tension in Y is the same as that in X. Okay, so they are both holding onto this weight. I would still sort of think, if you imagine you're holding the top wire or the bottom wire, you're still feeling the same weight. So C is the correct answer to this question. Okay, question 8. The diagram shows how the stress varies with strain for metal samples X and Y. Both specimens were stretched until they broke. So which of the following is, don't miss this bit, incorrect? So X is stiffer than Y. So stiffness is how much strain you get for the stress. So for the same amount of stress, Y stretches more. So the bigger strain on Y means that Y is less stiff than X. So that statement is correct, which means it's not the answer. X is a higher value of the Young modulus. Well, remember, the Young modulus is the stress over the strain. So it's the gradient of the graph. X has a higher gradient, so that is also correct and therefore not the answer. X is more brittle than Y. Remember, brittle is not to do with how easily things break. Brittle is to do with whether they deform plastically before they break. And if you look at X deforms plastically from this curve here, you can tell that. Whereas Y is a brittle material, X is not a brittle material, so X is not more brittle than Y, so that statement is incorrect. So C is the answer. Y has a lower maximum tensile stress than X. Well, you can see here, this is the ultimate tensile stress, so X is higher, Y is lower, so that statement is correct. So C is the incorrect statement. Question 10. So two wires X and Y have the same original length and cross-sectional area. The graph shows the extension produced by X and Y when a tensile force F is applied. So this is a forced extension graph, but they've got the same original length and cross-sectional area. So you can think of it as being a stress-strain graph, if you like. It would be exactly the same shape. So which statement? Again, we're looking for the incorrect statement. So for a given extension, more energy is stored in X than Y. Well, the energy stored is the area under the line. So for a given extension, here there is more energy stored in X than Y. That is correct. Bigger area under the line from X, this area, than there is from Y, this area. The Young modulus of Y is greater than that of X. Well, the Young modulus is the gradient of the line, so the gradient of X is more than the gradient of Y, so this statement is incorrect. So I'm going to mark that one as a B, but let's just carry on just to be sure. Both X and Y obey Hooke's law. Well, clearly they're both straight lines, so yes. While X has a greater breaking strength than Y, well, here we are, the breaking stress. This is the force. They've got the same cross-sectional area, so X has clearly got a higher breaking stress. Okay, question 11. Now, you don't often get trick questions in A-level physics papers, but this is a little bit of a trick question, I think. So, sample of wire has a Young modulus of E. A second sample of wire made from an identical material has 3 times the length and half the diameter of the first sample. What is the Young modulus of the second sample of wire in terms of E? Now, it's really tempting to start writing an equation here and going, oh yes, I can do this, E equals FL over AE, where's my numbers, where can I put in, oh, I've got half the diameter, that, oh, you won't catch me out with that, that's a quarter of the area, all that kind of stuff. But you don't want to be thinking about any of that. You just want to be thinking, it's the material, and Young modulus is a property of material. This is a bit like asking a question, of saying, you know, I've got a cube of ice and then I've got another cube of ice which has got 3 times the length and half the width or something. What's the density of the second ice? Well, it's the same density because it's the same material. In this case, it's the same Young modulus because it's the same material. Okay, question 12, which cannot be used as the unit for Young modulus. Well, we remember that Young modulus is stress divided by strain. Strain's a dimensionless quantity because it's got no units, because it's a length divided by a length. Stress is force divided by area. So newtons per meter squared is force divided by area. Pascals is another version of newtons per meter squared. 1 newton per meter squared equals 1 pascal. So it must be one of the bottom two. So if we look at the bottom two, the best way is to say newtons per meter squared. Can we turn those into base units? Well, a newton, force equals mass times acceleration, so that's kilogram meters per second squared. That's the newton in base units per meter squared, kilogram per meter per second squared, which is D, so that means the correct answer is C. That's the odd one out. Okay, question 13. So we've got a sine 0.8 meters long with a weight of 18 newtons. They've told us it's non-uniform. You can see that because the weight, the centre of mass, isn't in the centre. It's suspended by 2 vertical springs P and Q, springs by Hooke's law, and the spring constant of each spring is 240 newtons per metre. So the top end of P is fixed, so we've hung this off something, and then we've adjusted the top end of spring Q until it's horizontal in equilibrium. And we've got to work out the extension of spring Q. Now again, a little bit of a trap in here. P is really completely irrelevant. P is just holding this end up, so we could take moments about this point P, and this spring isn't really having an effect. It could just have been fixed to anything there, which just allows it to pivot. Excuse me. So if we look at the diagram, we can take moments about P, clockwise about P equals anti-clockwise about P. So the clockwise moment about P is the force of 18 newtons times the distance of 0.65 meters. The anti-clockwise is coming from the force provided by Q, and that force is the F at Q, let's call it, times 0.8. This means that the force at Q is 18 times 0.65 divided by 0.8, which comes to 14.625 newtons, just to leave all the decimal places in for now. And then we've got to work out the extension of this spring, so this is F equals KE, so the extension is the force divided by the spring constant, 14.625 divided by 240, and that comes to 0.0609, so 0.061. D is the answer. Okay, question 14. So we've got a wire W with length L, circular cross-section of radius R. W hangs vertically, a load is attached and bottom, it extends by E. Another wire X is made from the same material and has the same load attached to it. Which length and radius for X will produce an extension of E over 4? Well, if we say the Young modulus is FL over AE, we want an expression for E, the extension, so the extension is FL over AE. But the things that are staying the same here are the force and the Young modulus, because we're hanging the same weight and it's the same material. So the thing that's going to change it, if we just forget about our F over E, it's L over A, but of course A is pi r squared. So we're looking for a value of L and R which give us a quarter of the original. So we've got 0.5 over 2 squared, we've got 1 over 4 squared, we've got 2 over 2 squared, and we've got 4 over 4 squared. And the one of those that equals a quarter, so it's going to give us a quarter of the extension, is 4 over 4 squared. So that answer is D. And the last one, what name is given to a material that breaks without deformation when a force is applied to it? So this is a material Actually, I don't like this question. I think this should say without plastic deformation. So a brittle material is one that breaks without plastic deformation, but they've just put without deformation. So Beth will email me and tell me why that says without deformation as opposed to without plastic deformation. But the answer is going to be B, because B is the only one to do with breaking.